October 3rd, 2025. While NASA's Perseverance rover quietly captures a 20-frame stack of the Martian sky, the only sign of 3I/Atlas, a verified interstellar visitor, is a faint, ambiguous smudge right where it should be. Yet just as the world demands answers and high-resolution orbiter images, nearly 15,000 NASA scientists are suddenly furloughed, and all official feeds fall silent. It's the perfect storm: unprecedented anomalies, wild theories about a cylindrical object, and a blackout at the very moment latest images reveal something weird about 3I/Atlas. But what is being hidden, and why does every new claim seem to clash with what we thought we knew about interstellar objects? The story starts with a single blurry thread, but unravels into something nobody expected. Within hours of the Perseverance stack surfacing online, a single frame, barely more than a faint blur, became the spark for a digital wildfire. Citizen astronomers pored over raw data, overlaying the predicted ephemeris of 3I/Atlas against the Martian sky. The alignment was uncanny. The smudge fell exactly where CNEOS teams said it should. Yet the image's ambiguity proved irresistible. On X, users drew thick red ovals around the elongated feature, labeling it a cylinder or cigar and urging others to enhance the pixels. Within a day, the meme had mutated. Now, the object was a Martian monolith, a spacecraft, or a cosmic thumb drive. The original stack, a 20-frame composite, was dissected and reposted with every conceivable filter. Some threads claimed to spot surface markings, others insisted on a metallic sheen, and a few went so far as to trace supposed shadows, building a case for artificial geometry. Amateur sleuths began comparing the Perseverance data to older comet images, arguing that no known comet ever looked so perfectly straight. Each new repost added another layer of speculation, and soon, the cylinder narrative drowned out technical explanations about cosmic ray hits or image noise. Astrometric overlays circulated in Discord science servers, with some users carefully matching the faint streak's angle to the predicted motion of 3I/Atlas. The match was close enough to satisfy some, but for others, the lack of high-resolution orbiter images became the real mystery. Why, they asked, did the only available evidence come from a surface rover when Mars hosts a fleet of orbiters equipped with powerful cameras? As the meme gained traction, it drew in a wider network: space enthusiasts, skeptics, and conspiracy theorists alike. The absence of official imagery only fueled the fire. Each unanswered question was met with another viral post, and the boundaries between genuine inquiry and online spectacle blurred. In the vacuum left by silence, speculation flourished, and the demand for answers grew louder with every retweet. In August, before 3I/Atlas became a trending topic, Birdie Dworsky and her remote viewing team sat down with a sealed envelope and a set of coordinates. The session logs, time-stamped and posted days before the Perseverance images, describe something oddly specific: a device, thumb drive-sized, embedded in a much larger icy mass. According to the transcripts, this object was not inert. It pulsed, sending out regular, directed bursts. The motif of a technological core hidden within a comet-like shell recurred across multiple blind sessions, each conducted without knowledge of the target's identity. What stands out isn't just the device's scale or the pulse motif, but the language used. Viewers described masking, as if the object's true nature was deliberately concealed, and referenced surface graffiti or inscriptions, details that would later echo in online debates about artificial geometry and markings in the Perseverance stack. The overlap is striking, but the timeline matters. These motifs appear in logs from August, weeks before the first public hints of a Martian flyby or the viral cylinder meme. Still, remote viewing is not a recognized scientific method. Its claims, no matter how detailed or prescient, do not substitute for direct measurement or peer-reviewed data. On October 1st, NASA entered a partial shutdown. Roughly 15,000 staff, engineers, data analysts, even science communicators were officially furloughed, leaving only a skeleton crew to keep the International Space Station and Artemis systems running. For Mars, this meant a sudden bottleneck. Imaging campaigns for 3I/Atlas, proceeded as scheduled, but the teams who process, calibrate, and release those images were largely offline. Raw telemetry continued to trickle in from orbiters and surface assets, but without the usual pipeline, what reached the public was incomplete and unverified, a digital backlog accumulating with every orbit. The Deep Space Network kept its scheduled passes, relaying fresh data packets from MRO, Mars Express, and TGO. Yet, each downlink arrived to a muted response. Science centers in Pasadena and Darmstadt were operating on minimum staff, with most personnel locked out of their systems. Automated scripts archived the data, but manual review flagged a series of problems: pointing errors, compression artifacts, and suspected cosmic ray hits, none of which could be cleared without the full team present. ESA confirmed their Mars Express and TGO runs had succeeded, but held back public release, citing the need for interagency cross-checks and artifact analysis. The result was a vacuum, quickly filled by speculation and frustration. Into this gap stepped Avi Loeb, whose media appearances became a rallying point for transparency. He called for immediate release of all Mars-based imagery, arguing that the faint Perseverance signal, while intriguing, demanded independent verification from the high-resolution orbiter fleet. Loeb's checklist of testable anomalies, aired on podcasts and news segments, pressed the agencies to act. Meanwhile, discord grew online. Amateur astronomers traded DSN schedules and ops memos, trying to reconstruct the missing picture from whatever scraps they could find. The operational gridlock turned a routine data flow into a high-stakes waiting game, where every hour of silence deepened both the mystery and the public's impatience. 7 distinct anomalies now define the 3 I/Atlas's mystery, each measured and scrutinized by teams worldwide. The first, mass. Astrometric data, confirmed by CNEOS, reveals a nucleus so massive that even as it vents gas, its trajectory shifts by less than 15 meters per day squared, barely a blip compared to typical cometary deviations. Second, Hubble's imaging shows a coma that stretches sunward, not away from the sun as solar wind physics would predict. Instead of trailing dust and gas, the extension points directly at the sun, suggesting unfamiliar scattering or perhaps active thrust. Third, the VLT's spectrographs detect strong nickel emission lines, while iron remains nearly absent. In solar system comets, iron and nickel appear together. Yet here, nickel dominates, a chemical signature more reminiscent of industrial residue than cosmic debris. Laboratory checks confirm the ratio, but no known process accounts for it. Polarimetry brings the fourth anomaly. At a 7-degree phase angle, polarization measures -2.77%, with an inversion near 17 degrees, well outside the norm for catalogued comets. Multiple teams flag these readings as outliers, resisting classification. Fifth, the orbit. 3. I/Atlas follows a near-zero inclination, hugging the ecliptic and threading a path for close encounters with Venus, Mars, and, if predictions hold, Jupiter, all within a single solar pass. Such a low-inclination trajectory is statistically rare for an interstellar object. Sixth, the timing. Ephemeris calculations show the object's approach aligns with planetary conjunctions in rapid succession. The odds of this sequence occurring by chance are slim, unless the entry was pre-aligned long before discovery. Finally, coordinate overlays place the trajectory within 9 degrees of the 1977. WOW signals origin, a proximity that, while circumstantial, fuels speculation and prompts targeted radio observations during the December window. Taken together, mass, coma, chemistry, polarization, orbit, timing, and sky position, these anomalies resist easy explanation. The next phase, rigorous testing at Perihelion and during December reacquisition to determine if this stack is coincidence or the mark of something unprecedented. October 29th stands as the critical date. Perihelion, when 3I/Atlas sweeps closest to the Sun at 1.36 astronomical units. For weeks, every anomaly, every rumor, converges on this moment. Mars orbiters, still silent in public channels, are scheduled to capture their highest resolution frames as the object accelerates to nearly 68 kilometers per second. But the test isn't limited to a single day. Beginning November 2nd, the JUICE spacecraft enters its dedicated observation window, an unprecedented chance to monitor the aftermath from a unique vantage in deep space. For nearly 3 weeks, JUICE's suite of cameras and spectrometers will scan for outbursts, fragmentation, or any hint of non-natural activity, a campaign confirmed by ESA and tracked by mission planners in real time. As the sun's glare fades, Earth-based telescopes prepare for reacquisition in early December. David Farnokia from JPL's Center for Near-Earth Object Studies frames this as the true verdict. Only with fresh parallax and trajectory data can teams confirm or refute claims of non-gravitational acceleration. December 19th, when 3I/Atlas makes its closest approach to Earth at 1.8 astronomical units, is the final checkpoint. A global network of observatories, radio dishes, and amateur astronomers poised to catch the outcome. The calendar is set. Each date brings a new layer of testable evidence, moving the story from speculation to measurement. Peer-reviewed SETI calculations put hard numbers on the question of artificial signals. To replicate a WOW-class radio beacon from the outer edge of the solar system, say 600 astronomical units, a transmitter would need to output at least a megawatt, sometimes much more. That's the power consumption of a small city, focused into a narrow beam and aimed with precision. For any icy body drifting through deep space, this requirement strains credulity unless there's an obvious, detectable energy source. No comet, asteroid, or known natural process comes close to generating that kind of directed radio power. Probability debates around 3I/Atlas now hinge on how to weigh the stack of anomalies: mass, nickel chemistry, sunward coma, orbital alignment. Bayesian analysts start with a vanishingly small prior for artificial origin, less than 1 in a million. Then ask if each new outlier is truly independent. If so, the odds shift dramatically. If not, the case remains weak. Mainstream SETI researchers caution against multiplying improbabilities without clear separation. 7 oddities in one object sound dramatic, but unless each is both real and unrelated, the cumulative odds barely budge. For now, the only honest confidence meter is set firmly at not impossible, but not yet persuasive. The next round of data will decide whether this is a cosmic fluke or something that redefines the odds entirely. A micro-asteroid, 2025 TF, skimmed just 419 kilometers above Antarctica on October 2nd. It measured somewhere between 1 and 3 meters wide. Small by cosmic standards, but close enough to graze the edge of disaster. The warning came too late. 6.5 hours after its closest approach, the Minor Planet Center confirmed its passage, with orbit calculations so uncertain they earned a condition code of 7 out of 9. No alerts, no tracking, just a silent, streaking visitor. Planetary defense teams are left to tally the odds. How many more slip by unseen? On Mars, the Perseverance rover's sensors have picked up something almost as unsettling, but far more hopeful. In the Bright Angel and Sapphire Canyon regions, researchers have found organics tightly co-located with vivianite, a blue iron phosphate mineral known to preserve biosignatures on Earth. The rover's SHERLOC and PIXL instruments mapped these leopard spots in fine detail. The spatial overlap between organic molecules and redox-sensitive minerals is the strongest hint yet that ancient Mars may have harbored or preserved chemical traces of life. A paper in Nature Geoscience calls it the most promising biosignature candidate ever seen on the Red Planet. Yet, with NASA's funding locked in political limbo, even the sample return plans that could clinch the case are on the chopping block. Meanwhile, the Sun is restless. A series of coronal holes have unleashed solar wind streams topping 700 kilometers per second. Minor coronal mass ejections ride the fast wind, sparking G-level geomagnetic storms and auroras as far south as 40 degrees latitude. Space weather forecasters warn this may be the final surge before solar cycle 25 begins to fade. A last gasp, but one with enough energy to light up mid-latitude skies and test the resilience of satellites worldwide. A congressional hearing room flickers to life with a single unclassified video. A spherical object filmed over Yemen absorbs the impact of a Hellfire missile, and keeps moving. The official word is silence. Whistleblowers allege retaliation for reporting UAP incidents, and the Department of Defense offers no explanation. The debate spills onto every platform, blending uncertainty with fascination. In the night sky, 3 green comets compete for attention. C/2025X, known as Lemon, brightens into the naked eye range, with predictions placing it at magnitude 4 or even 3, rare for any comet in recent years. SWAN, post-Perihelion, favors southern observers, while ATLAS, still faint, rises in the pre-dawn north. Each owes its emerald hue to diatomic carbon and cyanogen, molecules that fluoresce under solar ultraviolet light. For a brief window, amateur astronomers can spot all 3, a triad not seen since the early 2000s. Meanwhile, Starship Flight 11 rewrites the script for reusable rockets. Booster B-15 nails a multi-phase landing burn, while Ship 38 survives a deliberate heat shield tile deletion and still relights its engines. A simulated Starlink payload completes the checklist. This marks the end of the V2 era. Future launches will use the heavier, more robust V3 design, promising even greater payloads to orbit. China's Tianwen-2 is already outbound, targeting Kamo-Oalewa, a quasi-satellite that may be a fragment of the Moon. After collecting samples, the craft will swing out to 311P, an active asteroid, in a decade-long dual mission that blends lunar science with cometary exploration. Yet, these triumphs unfold against a backdrop of institutional risk. With 15,000 NASA staff furloughed, only 3,000 remain to keep the ISS and Artemis missions alive. Proposed cuts threaten to cancel a generation of science missions, stirring fears of a brain drain as researchers look abroad. The future of US space leadership now hinges on political will as much as technical ambition. On October 3, 2025, Perseverance captured a faint smudge at the predicted position of 3.1i/Atlas during its closest approach to Mars, 29 million kilometers away, while over 15,000 NASA staff were furloughed, leaving high-resolution orbiter images unreleased. Scientific teams documented 7 major anomalies: a carbon dioxide-rich coma, nickel without iron in the gas, a sunward light extension, and an unusual polarization angle. Despite these findings, core questions remain. The missing orbiter data, the exact cause of 3I/Atlas's unique chemistry, and the nature of its mass and acceleration. Key observation windows, JUICE in November, Earth reacquisition in December, will deliver more data. But as of now, only fragmentary evidence is public. The story of 3I/Atlas is still unfolding, shaped by both hard science and operational uncertainties. Until the next round of images and spectra are released, the object remains a rare convergence of cosmic surprise and institutional silence.